Welcome. In this video I'm going to talk about gravitational force in general, and then Newton's law of universal gravitation more specifically. So when we were last together, actually the last couple times we were together, we have talked about centripetal force. And remember, centripetal force is not a separate force. That's any force, net force, or component of a force that acts towards the center of a circle. One of the specific forces we've talked about when we talked about forces in general was weight or gravitational force. And before we would define weight first we would define the letter H, looking a lot different from that. Equals m times g. That's basically the gravitational pull of the Earth on an object. That's what we said before. But we know that if you go on another planet or you stand on an asteroid, you're going to have a weight. That asteroid is going to pull on you. The moon is going to pull on you. Mars is going to pull on you. So weight being the gravitational pull of the Earth on an object, that's sort of an Earth-centric view. Because any object pulls on any other object. So the Earth isn't the only thing doing pulling in general. Any object has a gravitational pull on any other object. So what are those factors? So the pull depends on a number of things. It depends on your mass. It depends on the planet's mass, if we go back to the example of planets. And it relates to the distance between the two. So that's if we've got our planet, and then we have our person on our planet. So here's Earth. It's mass m. Here's a giant. And that was kind of sloppy. My uppercase M doesn't really look very much like an uppercase M. What about between a couple? You're pretty popular. You're taking a physics class. You're studying physics. So you've got an attraction to a certain group of people, perhaps people of the opposite sex, perhaps people of the same sex, depending on what you're interested in, but somebody's probably attracted to you. We're not going to talk about any sort of relationship attraction here, but you are going to be pulling on each other. So that means that this pull, so here we've got our boy and our girl. So it depends on the boy's mass. We'll call that little m. The girl's mass usually the larger mass is designated by the uppercase M, so maybe in this case the boy is a cross-country runner and the girl is a bodybuilder or shot putter, so she's got the greater mass. And then, of course, the distance between their centers. And we can abbreviate that by the letter R. So we've determined that that force is proportional to the mass of one object, proportional to the mass of the other object. And now what about distance? So it seems to make sense that the farther apart they are, the less that force is going to be. When we increase something and then its effect decreases, that's an inverse law. Turns out that gravity is what's called an inverse square law. So F is, so the gravitational force is proportional to mass of object 1 times the mass of object 2. So 1, 2, and the distance between them squared, inversely related to the distance between them squared. If we want to turn a proportion into an equality, we need to multiply through by a constant, and not just some arbitrary constant. What we would actually need to do, if we wanted to be super precise on this, is make a graph . And if we could graph F versus little m, big M over R squared, turns out that would be a straight line, and the slope of that line would equal this letter G here, this 6.67 times 10 to the minus 11th newtons meter squared per kilogram squared. And if we look at the units, we can see that, so the units, we're kind of squeezing things in here. I apologize for that. That's equal to kilograms squared over meters squared. And of course, the units of force is in newtons. So notice how these units here work out such that the meter squared on the bottom from the R squared term is canceled out with the meter squared in G. The kilogram squared from the mass terms cancels out with the kilogram squared here, and we end up with newtons as we must. So let's look at this force a little bit more. Does the Earth pull on all objects with the same strength pull? So if the Earth is pulling on two objects, and let's say we've got, I just took this from the book here, and I'm going to use a different color. We'll have a green object. And we've got the distance between them. And I'm going to call this M1, little m1, and this little m2. And little m1 is greater than little m2. So over here and here, let's just say this is the Earth. We'll call that the Earth. So the Earth's pull on M1 that's going to be, and the green's a little bit hard to see, that's going to be G, which didn't look much like a G. G. So G M1M over R squared. The Earth's pull on M2, that's going to be F2 equals G M2M over R squared. And since M1 is greater than M2, that means that F1 is greater than F2, assuming these R's here are the same. I didn't measure it super precisely, but I meant them to be the same. So the Earth doesn't pull on every object with the same strength pull, but the Earth's pull on an object is equal to the object's pull on the Earth. So, no, but the Earth's pull on an object is equal to the object's pull on the Earth. Because look at, if we just write this equation here, so F of the Earth on 1, G M1M over R squared, F1 on Earth, G capital M, M1 over R squared, and these two terms are equal to each other, because it doesn't matter the order that you have these. If you multiply two things together, big M times M1 is the same as M1 times big M. And that's exemplified by these force arrows pulling the same. And this is from Newton's third law. Let's look at this classic question here then. So do all objects fall at the same rate in minimal air resistance, so minimal drag? Well, we've already determined that the Earth does not pull on all objects with the same strength pull. So that's kind of odd. So the hammer, if we draw this from the center of mass, this is the Earth's pull on the hammer. Here's the Earth's pull on the feather. So clearly the Earth's pull on the hammer is bigger than the Earth's pull on the feather, and that comes from this right here. So assuming that they're both dropped from the same height above the center of the Earth, r squared is the same for both. G is a constant. The Earth's mass is the same for both. The only thing different is little m. So for the feather, little m is small. So m for the feather is much less than m for the hammer. Notice I sort of made the two m's one letter. It's pretty tricky, huh? Okay, so the Earth pulls on the hammer more, so that means the hammer falls at a greater rate, right? Well, let's go to something more fundamental than this. Let's go to the net force equals m times a, which means that a equals net force over. So let's check out what it is for the hammer. So for the hammer, the net force is large. It's F sub h. But the mass is large as well. Over here, the force is small for the feather, but the mass of the feather is small as well. So it turns out that the acceleration is the same in each case. So for the feather, the Earth doesn't pull hard on the feather. But the feather is not difficult to change the motion of. The hammer's motion is difficult to change. But the Earth pulls on it hard. So they basically, the effects cancel each other out. So the acceleration is the same for each. Let's just do a couple applications of this then. So I should have actually made this print a little bit larger. It says, astrology, that unlikely and vague pseudoscience, makes much of the position of the planets at the moment of one's birth. The only known force a planet exerts on the Earth is gravitational. Well, we just said earlier that all objects produce a gravitational pull on all other objects. So we know in the operating room there are a lot of people. Most births take place in the operating room. Of course, some births take place at home. Very rarely does a woman give birth just completely on her own. Maybe it's just she, and maybe it's only the father there or a midwife there. There's almost always somebody else there. Of course, there are planets there as well. So calculate the magnitude of the gravitational force on a 4.2 kilogram baby by a 100 kilogram father who's 20 centimeters from the birth. So he's helping out, getting ready to catch the baby as it pops out. So let's look at that, and so we know that in general f sub g equals big G m times m over r squared. So f sub g equals big G 6.673 times 10 to the minus 11th, and that is a small number. This, by the way, is evidence. So the fact that this number is so small, that's evidence that the gravitational force is a very small force. Even though it's the dominant force in shaping the solar system, shaping galaxies, it's actually a very weak force compared to the other forces. In fact, it's outstandingly weak compared to the others. So there's G. So little m, that's the mass of the baby. Again, it doesn't matter what order we have them in, but I usually like to have little m be the smaller mass. And the distance between their center of masses is 0.200 meters, squared. That's going to come out to be a pretty small number, right? Because we're just multiplying by 100. That's still going to be tiny. Turns out it's 7.01 times 10 to the negative 7th newtons. This is a pretty good sized dad. This is a 220-pound dad. I don't know, that's probably about average now. Just wanted to keep the color scheme there the same. So here, so this is for the dad. And then here is Jupiter. So we can look up the mass of Jupiter. In fact, I think I'm going to change my little nomenclature here from G to D for dad, because dads are important. It was a bit of a self-serving statement since I'm a dad, but I think you'll allow me to say it. Oh, and I didn't put the units up here before either, so newtons meters squared per kilogram squared. So this time I will, just so we can see. So we've got the kid is, so we still have the kid. And now for Jupiter, we've got a much larger object. So Jupiter is 1.9 times 10 to the 27th kilograms. But of course, Jupiter is also a lot farther away. It's 6.29. Times 10 to the 11th meters, and that's squared. So you can see now we've got a much larger mass up here, and we have a much larger distance down here. This mass is larger by a factor of about 10 to the 25, because 100 is 10 squared. This is 10 to the 27th power. Down here we've got 10 to the 11th squared. That's 10 to the 22nd. Up here we had 0.2, so this is really a 10 to the minus 1. Looks like we're going to get something that is pretty close. And it turns out it's 1.35 times 10 to the minus 6th newtons. So the ratio force of the dad, so the gravitational pull of the dad to the gravitational pull of Jupiter is 7.01 times 10 to the minus 7th divided by 1.35 times 10 to the minus 6th newtons over newtons. So the newtons cancel. Oh, and by the way, over here, meter squared on top, meter squared on the bottom, kilogram, 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 end up with newtons. So the number we get is about 0.5. We could be precise, we could say 0.521, but that's really 0.5 because neither the dad nor the baby are just these crisp point masses. So interestingly enough, the gravitational pull of Jupiter, and Jupiter, this is the average distance, so sometimes Jupiter is a little bit closer, sometimes Jupiter is farther away. But the pull of Jupiter is roughly the same as the pull of the dad. So let's put that in a different color. So how can Jupiter somehow influence the kid at birth? When f sub j is so small? So this is evidence of why astrology does not work. Yes, that's a good number to remember, that the pull of the father or the doctor or the mother herself, although there aren't as many 100 kilogram mothers and her mass is kind of wrapped around the baby, so that's a little bit tougher to calculate. But why aren't they considered in horoscopes? We read about Jupiter being in the constellation Aries or something like that, but why don't we read about the doctor being in the constellation Breathing Machine, or the nurse being in the constellation X-ray Machine? Ooh, I think I've sensed a new money-making opportunity. Let's look at one more example. Some of you probably know this, but the sun is not stationary in space. You probably figured that, but you wondered, so what's happening? The sun is actually orbiting the center of the Milky Way galaxy once roughly every 2.6 times 10 to the 8th years. And it orbits, it's roughly circular orbit at 3 times 10 to the 4th light years. So if we have our Milky Way, so R equals 3.00 times 10 to the 4th light years, and that's the distance it takes light to travel in 1 year. And its period let's go back to the color black again. .00, oops, sorry, looking at the wrong number. .60 times 10 to the 8th years. So let me get my notes closer to me here. All right, so part A, calculate the centripetal acceleration of the sun in its galactic orbit. So we know that A sub C some pretty poor penmanship there. Equals V squared over R, or R omega squared. And since we're given period, we could figure it out either way, but the best way to do this is to first find omega. So omega equals the circumference divided by the time taken. Which is 2 pi r divided by the period, or 2 pi oops, sorry. I was thinking, I combined my two thoughts here. I had a couple notes. So this what I wrote there is actually V. So if we, and then I looked at a different part of my notes. So if we want to do this here, the circumference is 2 pi r which is the radius, so 3.00 times 10 to the 4th light years divided by period, which is 2.60 times 10 to the 8th years. But if we do this, we need to convert a couple things, which I haven't done yet in my notes. So convert light years to meters and convert, we can convert years to seconds. But instead, I'm going to use, instead of doing this, I'm going to use omega. And omega is equal to 2 pi radians over the period. So that's 2.6 10 to the 8th years. And then we want to get this in seconds, so we know that 1 year is 3.16 times 10 to the 7th seconds. So the years cancel out, and we come up with a small number, 7.65 times 10 to the minus 16th. So R is 3.00 times 10 to the 4th light years. And we need to convert that into the units of meters. So we can use our seconds again. 3.16 times 10 to the 7th seconds per year. And then since light year is a unit of time, r is equal to time times velocity, or speed, so we need to multiply by the speed of light. So, oops. Seconds cancel here, and the years cancel with the light years there. So this is really, let's go with the answer first. .84 times 10 to the 20th meters. So A sub c, which is our omega squared, is equal to 2.84 times 10 to the 20 meters times 7.65 times 10 to the negative 16th radians per second, so that's squared. So clearly we're going to be ending up with a small number because we've got 10 to the 20th times 10 to the minus 16th squared. That's going to be 10 to the minus 32nd. So we're in a very small negative number, or negative exponent, I mean. And that equals 1.66 meters per second squared. This is a very small acceleration. So even though the sun is moving around the center of mass of the Earth, is the center of mass of the galaxy, it still is not changing its motion by that much. So the question before here was, does this result support the contention that a nearly inertial reference frame can be located at the sun? Yes. So an inertial reference frame is a non-accelerating reference frame. So this is very nearly a non-accelerating reference frame. Okay, the second part was calculate the average speed. So V equals R omega. So that's 2.844 times 10 to the 20th. And omega was a small number, 7.65 times 10 to the minus 16th radians per second. But now you can see we've got 10 to the 20th times 10 to the minus 16th. That's actually going to be a large number. So 2.17 times 10 to the 5th meters per second. So that's 21700, is that right? 1, 2, 3, 4, 5. So that's 217 meters per second. That's about 460,000 miles per hour. So very fast. Okay, so important take-home messages. When two objects with mass pull on each other with a force that is proportional to each of their masses and inversely related to the square of the distance between them, we don't have an equality without this proportionality constant, which is really just the slope of the force versus little m times big M over r squared graph. The Earth does not pull on all objects the same, but the Earth pulls on the Moon with the same strength force that the Moon pulls on the Earth. Why do objects fall at the same rate? Well, the Earth pulls on them differently, but they have different resistances to motion, different inertias. So big pull by the Earth, big inertia, little pull by the Earth, little inertia, results in the same acceleration. Astrology makes no sense because Jupiter's pull on a newborn baby is roughly the same as the father's pull on the newborn baby. Not to say the mother's pull, the doctor's pull, the nurse's pull, and so on. I hope you enjoyed this astrology lesson with Bruce.